Greetings to you. We will continue our discussion on ion selective electrodes, and in my last class I had taught you about the limit of detection of the several ions using ion selective electrodes. I had also told you that it is we do not know any other technique which can determine the concentrations of the metal ions as well as anions at these concentrations. So, now I am going to describe to you the solid state ion selective electrodes. There what happens is in recent years lot of research has gone into making metal oxide semiconductors, that is known as MOS, metal oxide semiconductors, and these are basically semiconductors with field effect transistors. So, they have specific properties for conduction of the electrons and ions etc., and they are popularly known as MOSFET, metal oxide semiconductor field effect transistors have been developed, and these are something like solid state devices for carrying out the chemical analysis etc. They have been used quite a lot. Here a thin ion selective membrane, thin means really thin, of the order of about 10 raised to minus 4 centimeter or some micron size, maybe below micron size, that is interfaced with a thin MOSFET, that is the base, which is encased in a non-conducting shield. I will show you a figure something like this. Here you see the membrane at the bottom, red color. So, this contains the solid state ion selective electrode with a metal oxide semiconductor, both are sealed here in the membrane, and here other things as usual. This is an internal solution of the analyte, this is silver chloride reference electrode, and this is basically a plastic cylinder, small cylinder, and this whole thing looks like an electrode, okay, and this is sealed etc., etc., and then it goes to meter, and we have a connection from here, one more for the measurement completion of the circuit. So, the response time of such an electrode is defined as the time taken for the cell EMF to reach a value which is 1 millivolt from the final equilibrium value. So, the response time is obviously affected by the type of the electrode, and particularly the nature of the membrane, size of the membrane, thickness of the membrane, structure of the membrane, and all those parameters that define the characteristics of a membrane. It is also affected by the presence of interfering ions obviously, and any changes in temperature also, because most of these semiconductors have characteristics which are responsive to changes in the temperature. So, the response time is usually obviously affected by the all these things. So, whenever you use any MOSFET electrode, the manufacturer will prescribe to you the optimum time for minimum time for measurement. Sometimes the digital meter or digital interface through which we read the numbers screen, the digital screen is programmed to become active after a particular lapse of time, maybe 5 seconds, 2 seconds, 2 minutes, something like that. So, the instruction will say connect all these things, put your sample, measure the absorbance after 2 days, after 2 minutes. You can say measure the, you will get the reading after wait for 2 minutes, you will get the reading. So, that the whole idea is this MOSFET takes a little time for getting into equilibrium state. General details of the care and maintenance of such electrodes are usually given in the literature. This is what I was trying to tell you. So, when the membrane is placed in contact with a test solution containing appropriate ions, whatever we want to determine, that is hydrogen, Na plus, K plus, etc., a potential develops and affects the current flowing through the transistors between the positive and negative terminals. The measurements can be carried out with very small volumes of liquid and find application in biochemical analysis and intracellular measurements. This intracellular measurement means basically you can put the electrode inside a human body. You want to measure spinal fluid, you just make a hole here at the back, insert it and see what are the changes possible. Such intracellular measurements can be made with MOSFETs. And ion sensitive field effect transistors, these are known as ISFET. Ion sensitive field effect transistor electrodes have been specially developed for such purposes. They have been developed as non-glass. We do not want foreign material to be inserted which is not compatible with our blood, tissues, etc. So, it should preferably be non-glass, because if the glass breaks, there will be glass pieces hanging around inside the body which can cause problems, and they should be rugged and clog resistant. Such probes are required for working with liquids, semi-solids and pH measurements under difficult conditions. So, ISFET and MOSFETs are one of the recent innovations in the ion selective electrodes. Biochemical electrodes are another set of electrodes. Basically, they are all ISCF. An increasing number of electrodes are being developed for such things. What they do is to convert chemicals into ionic products, which can be quantified using ISCF. For example, look at this equation: CONH2 twice, H2O and water. These are all, water is available in our body 94%. So, water, wherever we want to deal anywhere in the body, water will be an essential component. So, CONH2 twice, this is the ion, and this is H plus. In presence of acid, ammonia will be released, and that will give you ammonium ion plus CO2, carbon dioxide. So, that is not cobalt, that is carbon CO, urea. So, the concentration of NH4 INH ions can be converted into urea present, because here we are going to measure NH4 plus as a response that can be converted into urea. CONH2 twice is urea, NH2 CONH2. That is how I remember the formula. Many people remember as CONH2 twice, or I prefer NH2CONH2. That also tells me about the structure of urea. So, if urea is there, acidic material is there, and then ammonium ions are released, carbon dioxide is generated, and the concentration of ammonium ions can be converted into urea present. The urease is an enzyme that is does this job of converting urea into ammonium ions. The urease is incorporated into a polyacrylamide gel. It is set in the bulb of the glass electrode and held in place by a nylon gauze, or it may be immobilized onto bovine serum albumin or even onto nylon. So, bovine serum albumin, when you heat it, it forms a sort of membrane. Nylon also we can use nylon membrane or any other membrane which will act as a support. So, the potential developed is given by E cell is equal to K plus 0.0295 log of activity of the urea. So, biochemical ISCs have been available commercially for penicillin, digoxin, etc. So, let us discuss a little bit about the instrumentation and measurement of cell EMF. This cell can be either pH meter or ISC meter, ion selective electrode meter. Okay. Basically, operation of all will be essentially same. So, direct reading pH meters are available using solid state circuitry. They are useful and more accurate to measure small DC potentials such as those from ISCs. The modern pH meter can read up to 0.001 pH. That is fantastic. Nernst equation makes it mandatory for temperature compensation, because if your accuracy required is 0.001 pH, obviously it will be a function of temperature. The Nernst equation, no, RT by NF, RT by NF ln H plus. So, T temperature has got a direct effect on the quality of the pH determination, accuracy of pH determination. So, we want to make it a temperature, whatever temperature we measure, we need to compensate for the temperature difference from the normal measurement systems. So, this needs a biasing control, which is something to do with electronics, and electronics people, if you tell them that you need a biasing control for temperature correction, they will do it for you. And I am not going into details how such a circuit can be made or what sort of components go into that. That will be part of electronics, who will, if you are studying electronics, you will be knowing about such things, but such things should be available in the market shelf. So, all you got to do is buy that chip and then fix it into the meter, pH meter. So, the biasing control will be there. So, whatever is the temperature, suppose room temperature is 25 and today's temperature is 30. So, you can make the compensation by turning a knob, and then it can be manual or it can be automated also. There is nothing very special about adjusting a knob using correct temperature and calibration. Nowadays these things are done automatically and it makes lot of sense. So, some instruments include a slope control. So, what is a slope control? If a meter is calibrated around pH 4, a measurement of 9 would introduce some sort of error. This I have already told you, isn't it? So, in the alkaline range, the error can be as much as 1 unit around pH 12. So, what we need to do, every time I want to standardize a pH meter, I need to use a buffer. So, what is the buffer? What should be the pH of the buffer which we want to use for standardization? We need to use a pH 4 buffer, that is potassium tartrate, phthalate. Potassium hydrogen phthalate is a standard material. Even that potassium hydrogen phthalate is available in the market as small tablets, which you can dissolve it in 100 ml, use it as a buffer, standard buffer. So, we use a calibrated buffer at pH 4, and then I want to measure a pH around 9.2. We know that it will not show the correct pH. So, in such case what do? We have to adjust slope to RT by NF. What is RT by NF? R is gas constant, T is temperature, N is number of electrons and F is Faraday. So, whatever number you get, that should be the slope. So, if I adjust the slope to RT by NF value, then it is adjusted in such a way that a pH of 9.2 buffer should be read correctly as 9.2. That means 9.2 means 9.20. Here also it must read 9.20, not 9.3 or 9.4 or 9.1, but 9.20. I have decided not to write one more 0 here, because most of 90% of the pH meters are accurate to the second decimal. I am rounding it off. So, 9.20 should be read as 9.20 only. In such case, slope control is adjusted to read 9.20 accurately. Then again pH 4 I have to wash it, change the solution from 9.2 to remove it, wash the electrode 3 times, 4 times, 5 times, 10 times, because it is buffer. So, buffer will not change after one wash. The pH of the buffer will not change after one wash. So, you have to wash it number of times, dry it using a tissue paper, not an ordinary paper or filter paper, that will leave scratches on the membrane. So, such things should be avoided. You have to just pat it dry using tissue paper. So, wash it 4-5 times, pat it dry with tissue paper, throw the filter paper, again wash it, and then put pH 4 buffer, and then assume that the pH 4, if you adjust it like that, if it shows pH 4 again, you are ready for measurement of the pH in between solutions. So, what is the mode of operation for pH and ISC meters? Very simple. All you got to do is switch it on and let it warm up. Normally in 90% of the laboratories, what happens is we come to the laboratory, put the machine on, and whole day it will be on as long as we are working. Only when we go home, we switch it off and then go. It does not require a lot of current or any other care, except that we have to make sure that the water should be the electrode must be in contact with the water all the time. So, whenever you want to measure, you just have to remove that water, put your sample solution and check. So, we standardize the pH meter once in the morning and maybe in between if necessary, otherwise next day morning they can do that. Many people do it once in a week or something, that is also possible. And usually when we have buffer, the life of a buffer can extend up to 6 months. Sometimes the buffer will develop fungus. So, you will have to just filter it and use the buffer regularly. So, all those things are part of the instructions, and instruction manuals will tell you how to take care of buffer, how to standardize and all those details. Here I am giving you only a bird's eye view of the maintenance of ISC meters or buffer meters. I have seen in many engineering colleges and even arts and science colleges, people do not know how to take care of the electrodes. 99% of the time, whenever I visited colleges and they show, sir, this is our pH meter, I always see that the pH meter is dry, and if the pH meter is dry, you will never get a proper reading out of that. And same thing goes true with ion selective electrodes also. So, if you take care of the machine, machine will take care of you. So, that is why I am writing this slide especially for your benefit. If you are part of the teaching faculty or part of the laboratory, make sure that your laboratory, if it has a pH meter or ion selective electrode, keep it properly, so that every time you are ready to use, it should be available. If the pH electrode is dry, then the ion exchange capacity will go down and you may never get the correct pH. So, we always advise, always keep this electrode in a solution, in a beaker, dipped in a beaker. Come and top it up once in 2 days, once in 3 days, make sure that the water does not dry in the beaker, and electrode also should not dry in the beaker. Sometimes what happens is, if the for some reason electrode is dried and you are not able to use it, we dip it in HCl solution of about 1 molar solution and then keep it for a day or two and then try it. If it does not work, you have no other go except to throw it out and buy another electrode. Okay. So, getting back to this slide, the normal procedure for operation of ion selective electrode is switch it on and let it warm up, adjust the temperature control of the day. Maybe in India everywhere approximately 25 degrees centigrade should be ideal, maybe 30. 27 is also okay, 27 is average in India. Adjust the pH of the, after putting the temperature control, you have to adjust the buffer pH of the buffer solution to 4 and adjust the meter to read the pH 4. Then you can remove the buffer, wash the electrode properly like what I have described earlier, and then test the solution for pH. Use only tissue paper to tap the membrane dry. And then after measurement, place the electrode in distilled water and do not allow it to dry again. So, how do I operate a fluoride meter? Essentially same thing. Here what we do is prepare 0.5, 1, 2, 10 milligram per liter of standard fluoride ion solution. You open any textbook, they will describe to you what salt of fluoride you should use and where it is available and what should be the quantity dissolved and how to make that solution. So, I assume that you all know such things, and then so now I am putting it as a first sentence: prepare 0.5 ppm, that is milligram per liter, and then 1 milligram per liter, this is double, and then 1 to 2 again 100% double, and 2 to 10 500 times double, 500 times, is not it, 2 to 10 5 times. So, 5 to 10 up to 10 milligram, from 0.5 to 10 milligram per 10 ppm you can use a prepare standard fluoride ion solutions. Then what else you need? You need a TiSAB solution. It is nothing but cyclohexane diamino tetraacetic acid. So, you have to mix 57 milliliter of acetic acid, 58 grams of sodium chloride, 4 grams of cyclohexane tetraamino diamino tetraacetic acid, and then 500 ml of distilled water. You have to adjust the pH to 5.5 and dilute to 1 liter with deionized water. We do not want any ionic strength to be changed whenever we want to prepare such samples. So, we use only DI water for dilutions. Then we can prepare out 10 milligram per liter of fluoride solution, add 25 ml of TSAB solution, measure the EMF using reference electrode. Reference electrode usually is available, or you can buy one, or it is incorporated in the fluoride meter itself. Then we have to, all we have to do is press the button, measure the EMF using a reference electrode for all the standards, note down the reading whatever it comes, draw a calibration curve of EMF versus concentration and determine the concentration of the unknown. In modern gadgets, what do? Is they store the calibration curve in the memory. Assuming that all other parameters are constant, then if everything is stored, all you have to do when you go on a field test is you just take the sample, dip your fluoride meter, simply read the concentration. It will measure the EMF, refer it to the calibration curve stored in the memory, and it will display the concentration directly onto the display screen. So, now I want to describe to you what is a grand plot. A grand plot is a very simple system measurement of measuring the RT by NF value, that is the slope. Usually we say RT by NF 2.303, RT by NF is the slope of the electrode in contact with a solution when we make the calibration curve. But if anti-log of this quantity NF divided by 2.303, this is the sort of RT by, this is not RT by NF, this is NF by 2.303 RT, 1 over RT is plotted against reagent volume, we should get a straight line. This is a very simple concept. So, when this line is extrapolated, it cuts the horizontal axis at a point corresponding to the concentration of the test solution. So, grand plots papers are available commercially because you have to plot the anti-log value of NF by 2.303 RT. So, here is a grand plot for you, and here on the x axis we have a titrant base volume in ml, and then this is the x intercept. The grand plots are here, now RT by NF values, anti-logs, and this is in acidic medium. See how beautifully the whole series of points are connected. So, here it is acidic grand function on the left side, and with the red one we have the alkaline grand plots. So, the slope of the alkaline solution is minus OH minus, then 10 raised to minus B by Kw, and this is the other one. Here is the potential on both sides, and the intercept is the concentration of the substance, that is volume. So, such grand plots, if you refer to any research papers based on ion selective electrodes or the pH metal ion electrodes, you will come across several such presentations where they refer to grand plots. Do not get confused, it is only the slope, anti-log of the slope plotted against reagent added. So, it is easy to handle the signal, that is why. So, here we complete our discussion on the ion selective electrodes, and we go into another concept of the electrochemical technology, that is electrochemical sensors. Slowly we are moving from basic electrochemical technology of measurement of voltage, current, etc., on to this potentiometry, precipitation reactions, redox reactions, polarography, conductometry, and then Carl Fischer titrations, ion selective electrodes. Now we are moving into the world of sensors. So, after this we will be dealing with the process effluents and other things, and the electrochemical sensors, I have to tell you that the oldest electrochemical sensors date back to 1950s, almost 70 years before they were already there, and they were used for oxygen monitoring. I had described to you the oxygen membranes, as those things were being measured even around 1950s. More recently, the OSHA, Occupational Safety and Health Administration, began requiring the monitoring of toxic and combustible gases in confined space applications, and new and better electrochemical sensors have been developed. This is very important because confined spaces there is always a danger of someone getting confused, someone getting hurt if there is not enough oxygen. For example, if a sewer or something is to be repaired, a person goes down the sewer, there is no oxygen, lot of hydrogen sulfide will be there, he will suffocate and die. Such things we keep on seeing in the newspapers all the time. So, we also come across situations where a person is confined in a particular place, especially mines. In a very confined space they keep on working, and the oxygen level needs to be monitored very regularly. Whenever combustion is taking place, we want to measure the what is the oxygen available for combustion, because oxygen is a must for combustion treatment. So, by the mid 80s, miniaturized electrochemical sensors became available. It is not very far, we were all students at that time, and then they were all new gadgets, exciting gadgets for measurement, and many of our colleagues were working on the electrochemical sensors at that time in R&D laboratories, and we were all witness to developments, exciting developments in the world of miniaturization as well as electrochemical sensors world. Nowadays it is a world of sensor, because wherever any monitoring is to be done, we say why do not you put a sensor there. You want to measure the temperature on the above the surface of the earth, 20 kilometers above the earth, we say okay, put a balloon, put a sensor there in the balloon. So, switch it on when it goes to 20 kilometers. So, you want to measure how much is peroxyacyl nitrate in the stratosphere, put simply a balloon, send the balloon there, and then switch it on, and then measure the altitude, measure the sample, peroxyacyl nitrate. Like that, thousands of sensors for various chemical entities have been developed. They are available in the market, and there are not many made in India. In that concept, in that aspect, India is an underdeveloped country anyway as far as technology is concerned, and many of the detection for toxic gases, even now they are not available in India. Recently I wanted to measure the sulfur dioxide and then VOC, volatile organic carbons in an environment about 300 meters above the earth coming from a stack, but there were no Indian equipments available for monitoring such VOCs. What is a VOC? VOC is a volatile organic carbon. Many of the organic carbons, many of the organic solvents below the boiling point of 350 degrees are referred to as VOCs. 90% of the petrochemical combustion gases would be VOCs, and any solvent is a VOC. Among the VOCs there are methane based and non-methane based. Non-methane based would be aromatic solvents and maybe aliphatic solvents also, but those based on methane are CHCl3, CH3Cl, and then CH2Cl2, and like that. They are all ozone damaging compounds. So, in general VOCs are classified as methane and non-methane VOCs. I found out that when I wanted to measure organic solvents like methanol, acetone, acetaldehyde, and then ketones, not one electrochemical sensor was available for measuring their concentration at high altitude. So, anyway, but such things are available in the market. There are people who will import them and sell it to you, and the detection for many different toxic gases in PEL ranges with the sensors exhibiting good sensitivity and selectivity. So, miniaturized sensors are available and they would be, I have shown them here. So, the sensor, you can see the sensors here, very small sensors, maybe about 5 centimeter, and this could be about 10 centimeter. Here these are all 2 centimeter, etc., etc., and such sensors are available, very easy to fit in electrochemical circuitry, and they can show you the data on a display screen in wherever you are sitting at a long some other distance. So, it is like having a camera for a detective camera in a particular place. So, this will be a detective sensor for particular specific chemicals, and a variety of chemicals, electrochemical sensors became available for the detection of toxic gases, and then with sensors exhibiting good sensitivity and selectivity. Currently, a variety of electrochemical sensors are being used extensively in many stationary and portable applications for personal safety. You can even carry a sensor in your pocket, and you can carry many of the sensors on your body. For example, I am carrying a microphone here, but I can carry, you can see my pen here. I can carry, instead of the pen, it can be a sensor. If I am a mine worker, I can put it here and go down. The sensor will catch all the radiations coming from the earth. There are a lot of radiations called something like radons and radioactive material. I can pick it up, and then if the radioactive component from in my body goes up, I will be put out of action for some time until the radiation level comes down. So, it is important to measure not only the physical parameters such as this temperature, pressure at the working places, and then radiation levels, and then oxygen level, nitrogen, carbon monoxide level, and all those things. Fire people would be terribly afraid of carbon monoxide and carbon dioxide also. So, wherever there are fire chances, carbon monoxide and carbon dioxide sensors are required. So, the physical size and geometry and selection of the various components and construction of an electrochemical sensor usually depends on its intended use. We will continue our studies on the sensors in the next class. Probably I will explain to you more about their functions. We will not go into details of the manufacturing, because basically most of them would be based on electrochemical sensors like membranes and other things, which we have already discussed in the previous class, that is ion selective electrode. Thank you very much.